Software Engineering Radio, episode 44, interview with Brian Goetz and David Holmes. Welcome everybody to a new episode of Software Engineering Radio. This is another episode on concurrency. However, it's not a normal episode. It's an interview episode with two people who are quite famous in this area. One is Brian Goetz and the other one is David Holmes, both from Sun Microsystems. And we're going to talk about some advanced topics of concurrency. So, welcome. And maybe let's start by introducing yourself a little bit, what you do for a living.
My name is Brian Goetz. I'm a senior staff engineer with Sun Microsystems, and I've been a professional software engineer for the past 20 years. Recently, I've been doing a lot of work in software education. I've published over 75 articles on Java development, and most recently published the book Java Concurrency in Practice, which was the best-selling book at Java 1 to our great satisfaction.
And it's probably the best reading book on concurrency. I really liked it.
Thank you very much. We worked hard on it.
Yeah.
And so we're here at the Uppsala conference giving several tutorials on concurrency, as we've done in past years. And
my name is David Holmes. I'm currently working for Sun Microsystems, and at this time I'm an engineer in the Hotspot VM runtime group. I've been teaching concurrency in Java now for pretty much 10 years. It started way back in 1996 when I, shortly after getting a copy of Doug Lee's book on concurrent programming in Java. And there was a great demand at the time for teaching people about this new language and how the threading model worked and various others. There were a lot of misconceptions around in the early years, and it was something we thought would sort of pan out in a couple of years. Everyone would know how to do it, and 10 years later we're still teaching people. And we've expanded things a lot with the JSR 166 concurrency utilities, working on the book to Java Concurrency in Practice to get more information out. Yep. I really enjoy teaching people how to make effective use out of concurrent programming.
So let's look at some of the things we're going to discuss. Everybody knows that probably the most important thing in concurrent programs is to make sure they don't fail, in the sense that you have deadlocks, and so liveness is probably an important thing. So maybe let's start by discussing the difference between safety and liveness, and then discuss a couple of topics or techniques how you can ensure liveness.
Well, the basic safety versus liveness argument is very simple. Safety is to ensure that nothing bad happens, whereas liveness is to make sure that something does happen, preferably something good that actually has your program achieving the result that was intended. Yeah. And these two design forces are always they're always opposing each other, because typically the things that we do to make the program safe, introduction of locks, they tend to impact on the liveness, because while things are locked, they can't be accessed concurrently. That means activities are delayed, progression is affected. And conversely, every time we try to improve liveness by removing locks and doing things like that, if we're not extremely careful how we do it, we tend to introduce safety issues, because we remove a lock that should have been present. We now have concurrent access to something, and now we go from a slow correct program to a fast broken one. And that is the key thing that we have to try to avoid.
One of the real challenges of concurrent programming is that it fundamentally breaks the mental execution model that we were all taught in university.
We don't think concurrently.
That's right. We think sequentially. We think in terms of this abstract von Neumann system, and that's a great abstraction for teaching, and we've all internalized it quite well, but in reality, the reality is quite different. And so we're taught certain things that can go wrong, and we tend to think of those as the range of possible failure modes, but in concurrent programs, there's many things that can go wrong that can't go wrong in a sequential program. A sequential program could have liveness failures like infinite loops, but it can't have deadlocks or live locks or missed signals. Sequential programs can have all sorts of safety failures, which we just call bugs, but it doesn't have race conditions and data races. So everything that can go wrong in a sequential program can also go wrong in a concurrent program, and then there's a whole range of new things that can go wrong, many of which are subtle and confusing and unfamiliar. And to top things off and make it even worse, the things that can go wrong don't go wrong every time.
Yeah.
So in a sequential program, we can write a test, and if the test passes, we've developed some confidence that our program is correct. And if it fails, it fails repeatedly, and we're able to use that information to debug it. In concurrent programs, failures are usually rare probabilistic events, and that makes them much more difficult to test for, much more difficult to reproduce and analyze.
It's where the notion of a Heisenbug comes in, right? Whether the act of debugging something prevents the bug from happening.
Absolutely. And there are certain bugs that just will never happen on an Intel system, but they'll happen because Intel has a stronger memory model than, say, PowerPC. Mm-hmm. And so if you do all your development and testing on a Windows system, you may not see certain failures that would show up on other platforms.
Yep. So what are some of the techniques that I can use to prevent liveness problems, to prevent deadlocks? Any like 2 or 3 tricks or practices that people should try to to stick to?
Some of the key things with liveness, deadlock is one that always comes to people's mind, because as soon as you use locking, and if you overuse locking, you end up invariably needing to acquire multiple locks at a time. And as soon as you need to do that and you do it in the wrong order, then you can get a deadlock. So there are a couple of general rules of thumb for handling deadlocks, or for avoiding deadlocks. And the general rule for avoiding deadlocks is that you have to acquire multiple locks. You always try to acquire them in the same order. If you do that, then a deadlock is impossible. But imposing an absolute lock ordering on things, it can be done when you have entire control over the program. And it can influence all of the code, but sometimes it isn't always possible to do that. And of course, if you're developing in a component or a library, and that you know that you're acquiring a lock internally, and then you're accessing some other object, you don't know exactly what's going to happen in that other object, and at that point, you've lost any way to control the lock ordering. So one of the key design rules for writing components and library routines is to always try to avoid holding locks when you call out into other objects, other components. And this is what we call making an open call. The idea is that when you call out to someone, you don't hold a lock on the current object. So that object itself is still open for receiving further requests from other parts of the system. This not only improves the responsiveness of the object that's open, but it makes it impossible to get a deadlock by calling this other component, because you simply don't have the multiple lock acquisition.
And this illustrates the tension between safety and liveness that David was talking about. Many people, when they're first shown some of the things that can go wrong in a concurrent program, their first reaction is, oh, well, I'll synchronize everything and I won't have a problem. And as a solution, that's bad in 2 ways. One is that it's often not good enough to get the correctness that you're looking for, but also synchronizing everything means you're acquiring many more locks, you're much more likely to be acquiring multiple locks at the same time, and you're asking for deadlock trouble. And so one of the another way to think about how to avoid liveness problems is to have a global view of where am I doing things that are going to require locking, and can I sequester them into some smaller part of my program so I have less to analyze in terms of its locking behavior.
Okay, so another topic that I think is a little bit beyond what is probably known by everybody, which is probably synchronized keyword, are synchronizers, things such as latches, countdown latches, semaphores. So can you give us some overview of which kind of synchronizers there are, specifically then in Java 5 and also generally?
Yeah, so one of the things that we did as part of the JSR 166 expert group, this was the JCP group that specified the Java util concurrent package, is we looked at what are the sorts of mistakes that people make with concurrent programming, and what can we do to reduce those numbers of mistakes? And we identified that there are a number of patterns that appear over and over and over again in nearly every concurrent program. And so what we did was encapsulate these patterns into classes and allow people to specify what they're doing at a higher level of abstraction, providing them a known, safe, correct building block. And so examples of these higher level building blocks are things like Dijkstra counting semaphore, which is useful for bounding the number of of resources that you're acquiring, or the number of activities that are allowed to access a certain resource. Latches and barriers that are useful for allowing multiple parties to coordinate to solve a problem. If you want to wait until a certain number of players are ready to play a game, you need 8 players for the game, and the players arrive independently and say, "Okay, I'm here." You don't care what order they arrive in. You care about when does the 8th player show up?
Yeah, right.
And latches are a pattern that are used to implement something like that. And so there's a countdown latch class that was added to the class library. Similarly, barriers are useful in parallel iterative algorithms where you have broken a problem up into multiple subparts, and each thread is going to go off, do a little bit of work, but you want each thread to finish step 1 before anybody moves on to step 2. So a barrier is a common pattern used to implement this. And so by looking at how is it that people actually solve concurrent programs, what tools can we give them to make it easier to organize them so that they're less tempted to use the low-level facilities provided by the language, which are error-prone and hard to use.
Yeah.
So when you're writing a concurrent program, there are two key sides to the concurrent program. One is dealing with the safety issues, as we've said, which is all about figuring out your where your locks need to go and what you need to do to protect interference from happening on shared data. And then the second major thing is identifying all of the activities in your program, exactly what the threads are, what the threads are doing, and how to coordinate them. Because the second hardest problem is then coordinating the threads for what they're doing. You have producer-consumer situations where you have to wait for data to be available before you can process it. You need threads to get to a certain state before they can proceed with the next phase of computation. There are many, many different types of coordination situations that arise in programs. But the fundamental coordination protocol needed there can be abstracted out into these synchronizer classes. So using simple things like semaphores, countdown latch, cyclic barrier, exchanger is another one. Exchanger allows pairs of threads to meet together and exchange data.
Like an 8-hour rendezvous kind of thing.
Yeah, exchanger very much like a basic rendezvous mechanism for 2 threads. The cyclic barrier is a rendezvous mechanism for multiple threads. These very simple abstractions can be used to effect the communication coordination protocol for a wide range of applications.
So you mentioned an interesting term, and that is protocol. So if you want to build concurrent applications, you have to agree on certain protocols how the various parties access resources. And the problem is that compilers can't enforce these protocols. It's something you have to get right by design or review. And that's probably one of the fundamental challenges of building concurrent programs.
Yeah, that's very true. I mean, encapsulation is our friend here. If we can encapsulate the protocols inside the objects that need to enforce them. So locking is a good example. Locking is a protocol. If you have to rely on everybody who accesses the object to get the protocol right, then you're asking for trouble. You have a fragile program. But if you can encapsulate all of the ways to get to the shared state, if the shared state is well encapsulated and confined within some higher level service object, then the protocol is enforced by the service object and nobody can violate it. Communication protocols are a little bit harder because you like to write the activities themselves as their own abstraction, but then you have to explicitly write the communication between them. And depending on how the different activities are being written and who's writing them, you may be able to come up with certain handshake mechanisms that producer and consumer is a good idea. Producers know that they just have to shove a result somewhere, and consumers know they have to get a result from somewhere. And the abstraction we use for connecting them is just some abstract notion of a channel or a queue. And that's as much detail as they need to know about the mechanism, but they just need to know what the interface to it is. Other things are a little bit trickier. Threads that are involved in parallel computation tend to, they all know what's happening and they all know that they have to be agreed upon points where they have to synchronize. So depending on the situation, you may have to you may be able to internalize these protocols, and sometimes they're external ones. It's the way that you construct the application out of different parts, and you have to set up the communication links between them.
You already mentioned encapsulation, and I think a probably strong form of encapsulation, or maybe just a synonym, is thread confinement. So if you don't give out or make resources available to others, they, as you said, they can't violate the protocol. So we agree that coming up with the proper confinement of resources to certain parts of the program is one fundamental way of designing thread-safe programs?
Yeah, so the rule is in a concurrent program that whenever two activities access the same mutable data, they have to have a protocol for coordinating their access to it. Otherwise, they may step on each other. And so there are three ways to accomplish that. One is don't share. If only one thread ever has access to the data, then it doesn't have to worry about anybody else stepping on its data.
Right.
And this is what we call thread confinement. And this is how subsystems like AWT and Swing in Java achieve their thread safety.
And for example, parameters to stateless to methods that don't access any members are automatically thread confined. So that would be one way of doing that.
That's right. Any variable that is local to a method starts out its life as thread confined.
Right.
Now you could violate that thread confinement by publishing it in a shared collection, but as long as you don't take any step to make it visible and publish it to the heap where another thread might find it, you can be confident that it's not shared. So that's not sharing is one way of doing it. Another way of doing it is not mutating. If you have to synchronize to coordinate access to mutable state, if you don't modify the state, then you don't have to worry about one thread modifying it and stepping on the value that another thread is using. So you have sort of two ways to avoid the hard part. One is don't share, the other is don't modify.
Yeah.
And if neither of those approaches work for you, then you have to fall back to the old standby, which is synchronization. And that's hard to get right for exactly the reason that David was getting at, is that we have to invent protocols for coordinating access to shared state. It's not part of the language. Yeah. The tools the compiler doesn't enforce these protocols. And whenever you have multiple activities coordinating together, they're going to have to agree on a way to work together, whether it be accessing data or signaling each other when something has happened. And if these protocols are necessarily part of your program's design, and it's possible for your program to violate its own design.
Yeah. You said that one way of avoiding these problems is not modifying stuff, immutable objects. That reminds me of functional programming. So because it's side effect free, right? Whenever you change something, you actually clone something and then kind of apply the changes, so you create something new. Would you say, I mean, it's a kind of suggestive question, but so it seems like functional programming is a good way to writing good concurrent programs.
Yes, and that's one of the areas where good object-oriented design principles and good concurrent programming principles are in agreement. Another is what David just said, is encapsulation.
Yep.
Encapsulation is good for writing single-threaded programs, and it's even better for writing concurrent programs. Yes. And immutability is the same. Immutable objects are simple. You can't get them into an incorrect state. You can't violate their invariance. You don't have to worry about them changing unexpectedly. And so immutable objects are simpler. Now, of course, at some point, every program has some mutable data. Otherwise, it doesn't do anything. Yep. But if we can limit mutability to a smaller set of well-defined places, it becomes much easier to ensure that, yes, we're applying the correct synchronization protocol everywhere where we access the shared data. And the smaller a space that is, the easier it is to get your program correct.
And one of the things that people often don't realize about immutable data is that they tend to think initially that, this doesn't apply very often. There's not much immutable data. I have multiple pieces of state information in my service, and it's all mutating, and so immutability can't help me. But that's not quite the right way to look at it, because very often if you have a compound state within a service or an object, and you're exposing that state through a series of simple accessor methods, then what you're actually exposing is an inconsistent view of the object, because you never know whether the value of field A and the value of field B that you've just read as two separate operations, whether they actually reflect the same state of the object, or whether something is mutated, one of them in between. So often what you need to do in these cases is actually group your state together. You want to encapsulate the state.
As a compound object.
As a compound object, as what we term a split representation.
Right.
We actually want to represent that state as a compound abstraction that we can then present as an immutable snapshot. And immutable snapshots of state are a very useful and powerful tool.
Okay. We talked about liveness before. Liveness is obviously related to performance. The more lively your program is, the better it performs. So I would probably think that too much locking, as we said before, makes the performance worse. So what kind of optimizations are there that maybe, compilers or anything can optimize away locks?
Yeah, locking and performance definitely interact. And one of the key things, though, is that the issue is not so much the locking as it's the contention. If you really have high contention for data, then whatever mechanism used to protect it is going to cause a bottleneck, because the data is contended, so the data is a bottleneck. Right. But if when people start, as Brian said earlier, people have been sort of led down the path of naively locking everything, and you can very easily reach situations where you have so many levels of lock. It's like putting a padlock on your bedroom door and having a padlock on the door to the hallway, and putting another deadlock on the front of the house. And the street has an armed guard at the end of it with a large metal gate, and it's like everything is perfectly safe, but there's just a little bit too much safety there. There's a bit of overhead in trying to deal with all that. Some of the things that compilers are trying to do now to be a bit smarter about some of this stuff is lock elision and lock coarsening. And lock elision is basically removing locks. If the compiler can tell that an object is actually thread confined, good example, the early collection classes vector and hash table were defined as synchronized collection objects. And yet 99% of the time they're used in a thread confined way. The locking is completely redundant. It's useless. Now, VMs have gone to a lot of trouble over the years to learn how to decrease the cost of uncontended locking, so you get that almost for free. So the next step is to actually get it for free. If the compiler can tell that the object is thread confined, then just no locking occurs whatsoever. Right. And they can do this using escape analysis. And this is something that's, the literature has been, there's been a lot of literature on escape analysis over the years, and a lot of research languages have employed it for various types of system. But it's finally making its way into mainstream systems, so that dynamic compilers in runtime environments are trying to do some of this escape analysis so that they can do lock elision, and some other forms of analysis to do lock coarsening. That if you keep acquiring and releasing locks in a sequence of code, that you can actually remove the multiple lock uses and convert them to a single one, which actually has a potential impact on liveness. So it's not something you can do arbitrarily. Otherwise, you would just be tempted to remove all locking and put a giant lock at the beginning of everything, and that won't work. So there is a lot of research in this area, and
heuristics, I guess, and
a lot of potential optimizations for all of these over-optimized cases. Over-synchronized cases.
And when speaking about performance, it's actually very useful to divide performance into two separate components, and which often get conflated when people discuss it. There's performance and scalability, and these are actually almost orthogonal measures. So performance is what we're used to thinking about in sequential programs. How fast can I do this unit of work? Can I do it in 10 milliseconds instead of 12 milliseconds? Scalability is a different notion, and it's a measure of how much work can I do with a given amount of resources, and if I have more resources available, can I do more work? So ideally, if your program scales perfectly, if you throw 10 times as many processors or systems or disks or network pipes or whatever the critical element is, can I process 10 times as much work? And of course, no program actually scales ideally like that, but there are certainly some that do much better or much worse than others. And as multi-core processors are becoming ubiquitous, this is becoming a much bigger deal. A few years ago, a multi-way system might have had 4 or 8 processors. Now we're starting to see systems that can execute dozens or hundreds of threads concurrently, and the degree to which exclusive resource locks become a scalability bottleneck is becoming much, much more important.
Another topic I'd like to get to is, how do I test concurrent programs? We already talked about the Heisenberg effect. So if I write tests or debug something, the error that I'm trying to get at is not there anymore. So, I mean, what kinds of best practices are there for testing concurrent programs? Maybe except for hiring Doug Lee, maybe.
Well, that would certainly be an excellent start. The reality is that testing concurrent programs is extremely difficult for a number of reasons. One is, as I said earlier, concurrent programs are more complicated than sequential programs, so they're harder to test. the tests for concurrent programs are themselves concurrent programs. And since concurrent programs are harder to write, concurrent tests are harder to write.
Okay.
And one of the problems, especially when writing performance tests, is that the test programs may introduce synchronization or timing artifacts that perturb the behavior of the code being tested. And so it's not simply a matter of slapping the obvious test routine around the code being tested. Sometimes you have to work very carefully to craft an unintrusive test.
Right.
And tests for concurrent programs need to run for much longer and explore much larger percentage of the state space because the errors you're looking for are not simple errors like if I pass null to this method, it throws an exception, but if this thread does this and then this thread does that before this other thread does that, then we'll get the wrong result. And in order to set up interactions like that and give them a chance to occur, you have to run for much longer and with a much larger number of potential interleavings. And in some sense, designing tests that do this is a black art.
Yeah.
One of the ways to simplify the process is to limit the concurrent interactions in your system to a smaller part of your system. And so, as David was talking earlier about the producer-consumer pattern, one of the nice things about that is the producers, which are the activities within your program that are finding work to do, all they have to do is they don't interact with other producers usually. They find maybe they're crawling a file system or they're crawling a website, and they're each working independently. They identify a bit of work to do, and they stick it on a work queue to be processed. And the only concurrent interaction is is that part where the producer is putting an element on the queue. And similarly, on the other side, the consumer is taking elements off the queue and then likely doing something with it that doesn't involve interaction with other threads.
Right.
And so if you can structure your program so that the concurrent interaction is all there in the shared work queue, now you only have one thing to test. You have to test that your work queue performs correctly. And fortunately, there are some excellent implementations in the class library that have already been tested to death that you can use with confidence. And so by, again, sequestering the concurrent interactions in your program into a smaller area, you have a better chance of testing them.
Yep.
And just as with sequential programs, there are two key style of tests with concurrent programs, black box, white box testing. So the key thing with black box testing, often people just refer to as stress testing, is that you're really just exercising the external APIs of an object or a service.
Right.
And you want to try and throw as much concurrency at it as possible, and you hope that it exercises all the possible interleavings and interactions that might occur. Now, simply doing that and hoping doesn't really help, because it turns out that if you run it on a particular platform, your set of possible interleavings is just a small fraction of the theoretical set, and you'll get a different set on a different type of hardware. So there are some tools that people have been working on, and I believe it's Bill Pugh at the University of Maryland that has a tool for interjecting arbitrary interleavings of threads when code is running. So basically, is if you could force a context switch between any pair of instructions to actually generate the various interleavings.
Right.
Now, obviously, the number of possible permutations there means it's impossible to compute. But if you can introduce these interleavings to some random degree to get a much better coverage of what you're testing. And the second aspect is the actual white box testing, which is sort of more along the lines of what Brian was discussing previously, that if you understand the basic operation of the protocols that you've coded up and the interactions, you can try to formulate properties, say, if I get to state X and this happens, I should go to state Y. And the hard part of that is, how do you get to state X to actually initiate the test? And that's probably one of still the biggest outstanding challenges. And we tend to have to use a range of our own tools, a range of synchronizers when we're testing, for example, thread pool executor. We need to use latches and barriers and a range of other things to try and force the system into a particular state so that we can then test the property of the executor that we actually wanted to test. And that's extremely difficult to do. And we certainly could do with more research and more tool development in this area to try and assist in saying, how do I get to state X so I can test for the transition to state Y?
Yep.
And just a little bit of a plug here. There are some of these tricks that David was alluding to are described in greater detail in the testing section of our book, which, as far as I know, is one of the few places that actually addresses
explicitly
testing concurrent programs.
Yep. So how does the Java memory model, or more generally, what kind of support does the VM have to provide for concurrency, we already talked about lock removal as an optimization technique. What other aspects or interactions are there between concurrency and the Java memory model?
So the Java memory model is an abstraction that serves several purposes. One is that it specifies a least common denominator set of promises that the platform makes to the program, and this facilitates the development of thread-safe concurrent programs. That programs know that this is what I can expect from the platform, and if I code to this, my program is going to be correct on all Java platforms.
Yep.
It's also has been designed not only to provide a reasonable set of coherency promises to the program, but also to enable VMs to optimize code in sensible ways. So there's a tension in specifying a memory model. The stronger you make it, the easier it is to write programs, but the harder it is for a VM to optimize the program and do things like what David was talking about, such as removing locks or reordering instructions so that they can execute faster, etc. And so the memory model is something that a lot of programmers will just never have to see or deal with, especially if you use the higher level utilities that we've been discussing. And use the usage patterns that are recommended. These are designed to be thread safe, and you don't have to understand the details of the memory model. If you wish to squeeze that last little bit of performance out of the system, it's something that you then have to become more aware of, because you don't want to go to the point where you're relying on lucky timing in order for your program to be correct, and that's the danger when trying to optimize concurrent programs. You do things that look like they might work, or they look like they should work, but only according to a naive execution model, an execution model of a processor that is not like modern processors, because modern processors do some downright weird things to your code unless you tell them not to, and the primary way of telling them not to is to use constructs like synchronization.
Right. Yeah.
The most complicated part of the memory model that people tend not to realize is that it's not specifying what effects synchronization operations have on memory, because that's true. People have been doing that in different systems for years. It's easy to say, if you want this to work correctly, you use locks, you use pthread mutex, you use condition variables, and things like that. What the memory model had to do in Java was provide the additional safety guarantees that no matter how badly you screw up the synchronization in your program, you are not going to be able to break Java. You should not be able to crash the VM. You should not be able to circumvent security mechanisms that are inherent in the platform just because you didn't use a lock correctly. And that's a very important thing. If security can be circumvented just by failing to acquire locks the right way, then we don't have security at all. So the hardest part of the memory model is actually coming up with these safety guarantees. It's providing this safety net. And so the basic rule that they came up with here is the not out of thin air rule. It's whenever you write a value to a memory location, or when you ever read from a memory location, you will get a value that some thread at some point in time actually wrote there. And that's as strong as it gets. You will not get complete garbage. You will never see totally random bits in references and have pointers that go off into the wild blue yonder. So it sounds simple to say it that way. Actually specifying it was an awful lot harder.
So let's talk. I mean, the stuff we talked about until now is more or less traditional concurrent programming with locks and synchronization, and it's probably good practice among people who know what they do in this area. But there is another approach of concurrent programming, which where you'd find terms like atomic variables and lock-free concurrent programming and things like transactional memory. So what is all that stuff about? How can you write concurrent programs without locks after what we discussed till now? How does that work?
That's a very good question. I mean, this is all about performance, because if locks were cheap and free,
right,
and we never had to worry about deadlocks, we always took care of deadlocks, we wouldn't worry about it. We would just use them arbitrarily. They would just be taken for granted. It just wouldn't be an issue. But locks do have a cost, and we can't avoid the fact there is a cost there. And whenever we use locking, we are reducing the availability of an object or a service. And a lot of people have done a lot of research over the years, over the last 50 years now, that there are ways of defining data structures that can be safely mutated and accessed concurrently that don't require locks. Now, unfortunately, the internals of these data structures do not resemble your traditional notion of a data structure in any way, shape, or form.
Okay.
These are highly specialized data structures that are operated on by incredibly complex algorithms that invariably rely on very specific memory semantics, things related to the memory model. So the basic ability to have some kind of atomic operation, that there are some things you can rely on as being indivisible execution units, whether it's something that we all take for granted, that when you write to a register on a machine, or write to a memory location on a machine, that is an indivisible unit of work.
Yeah. So the idea is to have higher level things that are also indivisible, like check and act or something like that.
Yeah, you can't get very far with only single reads and writes. You need some kind of read, modify, write sequence that is exposed in some way by the hardware platforms. And this is what's happened. Ever since we've had multiprocessor systems, we've had mechanisms provided by different platforms to do some kind of read, modify, write sequence. And one of the common ways that's expressed is in a compare and set operation.
Right.
That if you read the value of some state, and you want to compute the next value of it, and then you want to replace the current value with the next value, as long as it hasn't changed in the meantime.
Yeah.
And the hard part there is as long as it hasn't changed in the meantime. This is the thing that you cannot compose out of smaller primitives. There has to be some primitive atomic operation that's provided to you. And so if you take an atomic operation like compare and set, then you can build up these algorithms and data structures to provide a high-level, totally concurrent data structure like a concurrent hash map that people could then use as a basic building block in their application, knowing that it's completely thread-safe, it's also highly performant, but sometimes with a few differences in semantics. If you've relied on having exclusive access to a data structure and then you write one that's designed purely for concurrent access, then you've lost that exclusivity if you happen to need it. But you get a lot of benefit from the high performance that you now get from these concurrent data structures. Yeah, and in the research, it even goes even further that if you manage to come up with a system that has a double compare and set, then the algorithms and data structures get even simpler, and you can introduce much more of them. But unfortunately, we don't have that in the hardware.
Right. So that's what I was going to say. That's requires hardware support, and the more modern processors probably have some level of support for that.
So if you want to try and generalize this, then you start to move into another realm, and that's the realm of transactional memory and transaction software. And I'll let Brian tell you about that.
Yes. So David talked about non-blocking algorithms. And these are algorithms that use, instead of using locks to achieve safety, use a finer-grained atomic instruction, generally compare and set, compare and swap, load, link, store, conditional. Every processor offers one of these. If writing correct programs with locks is hard, writing non-blocking algorithms is 10 times harder. A lock-free counter is trivial. A lock-free stack is fairly straightforward. And when you get to something as complex as a singly linked list, we're talking about the level of effort of a PhD thesis to prove that it's correct.
Okay.
So this is not something that the average engineer on the street is going to be coding up this weekend. So developing lock-free algorithms is extremely difficult and is really the purview of a very small group of experts. And so this is not really a viable way to achieve better concurrent performance only because so few people are going to be able to use it. And the only way in which lock-free algorithms are really going to provide better system performance is to the degree that they are encapsulated in system libraries. And much of the performance improvements in the class libraries going from Java 5 to Java 6 and Java 6 to Java 7 is the replacement of lock-based algorithms with lock-free ones. But you asked about transactional memory, so transactional memory is a concurrency control model that is still squarely in the research phase. So we're not going to be seeing systems anytime soon, mainstream systems anytime soon that use transactional memory. But the idea is to allow the programmer to specify what he wants, not how he wants to do it. So I'm beginning an atomic operation, do this, and that, and now that atomic operation is ended, and let the system figure out the fastest way to execute it. And so we saw this with databases.
Exactly,
Originally, databases used very coarse-grained locks that when one client was executing a transaction, other clients might be locked out, and then databases got much smarter about, well, this client is operating on this data and that client is operating on that data, and I can allow both of these transactions to proceed simultaneously. And similarly, most of the time, true contention for data is limited. If I'm working on this data structure over here, and
you can partition the data structure, then so you shouldn't have locks for a whole hash table, for example, but only for parts for it?
That's right. And it's impossible to do that with locks. It makes your algorithm more complicated.
Yeah.
And so there's always this trade-off between simplicity and performance. Single coarse-grained lock is simpler, but offers worse scalability. A larger number of fine-grained locks offers better scalability, but more complexity and higher risk of deadlock.
Yeah.
And the idea of transactions, software transactions, is we're trying to eliminate all that by letting the system figure it out. So rather than the programmer saying, here is the scope of contention, the data contention that I'm concerned about, you simply say, I'm starting an atomic operation now. You go and use some data, and the system figures out, well, what did you touch? Oh, you only touched this one variable. I can execute this transaction concurrently with these other transactions that aren't touching that variable. And you can think about the promise of this as being the same as the promise of garbage collection. With manual memory management, there's all sorts of mistake modes the programmer can make if they don't do it correctly, whereas with garbage collection, those mistake modes go away. The hope is that with software transactions, many of the concurrent interactions like data races and race conditions will go away as well. As far as how do we implement these systems so that they work and so that they are performant enough that we would actually want to use them to write real programs, this is still a research area.
Yeah. So since we're already looking into the future, let's maybe look some more to wrap this episode up. So one thing I got the impression during your tutorial and also during other reading your book and other discussions on concurrency, my impression very much is that current languages such as Java, including some of the libraries in Java 5, the language abstractions aren't good enough for concurrency. So you can't declaratively specify, for example, I mean, you can use, for example, the Java annotation that says, this variable is guarded by that lock, but there is no way how the compiler can easily verify that you actually always hold the lock when you access the variable. So the point is, do you agree or do you think that more language support, probably more declarative support for concurrent aspects of a program will make tool support easier so that compilers or other checkers can give you more meaningful messages about concurrency problems you're probably about to code in your code?
There's certainly an opportunity there. We always go through these phases where we have the mechanisms available to us and they are extralingua mechanisms that
idioms basically that people use.
Patterns, use of libraries, various protocols, and there is no built-in support. They're not part of a type system. They're not easily checked. And the next level is then to add some kind of annotation that some other tool can use to help to verify that our intention is, well, what we coded was what we intended to code. And there's certainly a lot of benefit for doing that. If the tools were available today, they'd be helping Java programmers for the next 4 or 5 years. And there's certainly there's some work happening in that area to do that. The bigger question there is going back to how we should be expressing and modeling concurrency in our programs. People. There is a long history of concurrency. When Java came along, there were a few critics who said, 20 years of concurrent programming history, and this is the best they could come up with. And that's fairly unfair, because if you look through the history of concurrent programming, you don't find any single solution that stood out that Java could have said, hey, this is obviously the way to do concurrent programming. There are lots of individuals who think that their way of doing concurrent programming was the way to do concurrent programming, but there was certainly no obvious preeminent way to do it in that space. But the goal is always to have these things be more declarative. What do I need to do, not how do I need to do it. Threads and locks is all about how. I want to do this concurrent operation. So if I want concurrency, I need threads. If threads are going to interact, I need synchronization. I need locks. It's all about the mechanisms. We're struggling at the language level with the mechanisms. And what we would like is something that simply says, do it. Even the do atomic of software transactions it's only one level higher than where we are, because we're still responsible for identifying where we need these interactions to occur. And the hope is that eventually we will have higher level languages that can express concurrency in more succinct forms.
Is there anything on the horizon, research projects people can look into? Or
Well, there are different things. I mean, the Fortress language that Guy Steele was talking about this morning is a very obvious concurrent parallel language. But its emphasis, as all of the nice, neat, declarative concurrent languages are always to do with scientific programming and data parallelism. It's not quite clear how you would use Fortress to program your typical middleware system doing distributed client message queuing and various things like that. I'm not saying it can't, but it's certainly far more obvious how to do parallel loop execution and number crunching, massively parallel computing, and that's always been a tension in this space. So at this stage, I don't see anything on the horizon for the environments in which Java is currently being used to do multi-threaded programming. There have been some attempts at various dialects to sort of improve the model to make it less amenable to all the errors, but you always lose some power and flexibility in doing that. So, I don't think we're going to be out of a job in teaching people about concurrent programming in Java for a little while just yet.
Another avenue for improving the quality of concurrent programs is besides tools and language support and all of that, is awareness that concurrent programming simply is harder than sequential programming, and a big challenge of that is just people recognizing that. And to some degree, the Java language plays a dirty trick on programmers in that the fundamental values of the Java language design are simplicity and safety. Many features of the language were designed to not allow the programmer to turn off safety guarantees. That it checks every pointer for null when you dereferences it. It checks the bounds of an array before you index into an array. It checks the type of an object before you cast it. And you can't turn these checks off the way that you could in previous languages. So the idea is we're offering a much higher level of safety, that if you do something wrong, we're going to throw an exception. We're not going to let you proceed with garbage data. And similarly, simplicity. We've the language design takes away many of the things that made C++ more complicated, multiple inheritance being the obvious example. And then there's threads, which are neither simple nor safe. If you have two threads access a variable without synchronization, you have data race, but it never throws data race exception. It just maybe does the wrong thing. And so you don't have that level of safety checks working for you the way you do with other mechanisms. And the aspects of failures in concurrent programs, that they're probabilistic events rather than deterministic ones, is something that undermines simplicity. And so I think part of it is simply recognizing that when you're working in a concurrent environment, this is harder. You need to be more careful. You need to code more slowly, carefully review your code, have your code reviewed by other people, document your design intent more clearly. And the example that you gave about the guarded by annotations, not only might that be consumed by tools to tell you that you've made a mistake, but it's also a documentation thing that tells you, here's what I was thinking when I was designing it, just in case I've forgotten between then and now. And then and now might be only a few hours, or it might be 6 months when you come back.
Or a different person.
Or a different person when they come back to maintain the software. And so realizing that you're in a more dangerous, more hostile environment, therefore you should be more careful, watch out for the pitfalls, work a little bit more slowly, not be afraid to ask someone to peer review your code. All of these things, while they're not magic bullets and they're not technological solutions, they are effective ways to improve the quality of concurrent programs.
Okay, so I think that pretty much wraps it up. Thanks for being on the show, and looking forward to some additional book on, other advanced concurrency stuff.
Thank you, Marcus.
Thank you.
Thanks for listening to Software Engineering Radio. If you want to get more information about Software Engineering Radio, or if you want to give us feedback, please go to our website at se-radio.net. You can also contact the team at team@se-radio.net. se-radio.net, although we prefer entries in our comments system on the website so other people can see what you think. Software Engineering Radio wants to thank Henning Pauli for the intro and outro music, as well as Libsyn for providing the bandwidth. This episode of SE Radio, as well as all other episodes, is licensed under Creative Commons license. See the Software Engineering Radio website for details.